Hello everyone, and welcome to this special presentation of Cisco Catalyst 3560 and 3750 quality of service. My name is Kevin Wallace, and I've done several Cisco training videos over the past year and a half or so, and as I've been doing those videos, I never really took the time to give you any of my background before we got started. I thought that that's not going to help you. Let's just get to the business of showing you something cool and teaching you something rather than talking about my background. But this video is a bit unique because it's lengthier than the typical videos I do. So I thought if you're going to spend this amount of time with me, you probably do want to know a little bit about my background. How did I get here? Where did I come from? Well, again, my name is Kevin Wallace, and currently I'm a full-time instructor of Cisco courses. I'm a Cisco Certified Systems Instructor, CCSI, number 20061 specifically, and I also write several books for Cisco Press. You see a selection of those titles at the bottom of the screen. Some of my more recent titles include the CCNP T-Shoot Official Certification Guide. I've done the videos, the video mentor portions of the CCNP T-Shoot Cert Kit and the Route Cert Kit for people just getting into the world of voice over IP. I wrote the Voice over IP First Step book, and I've written the second, third, and fourth editions of the C-Voice book from Cisco Press. And more recently, for Pearson IT certification, I authored the Network Plus book for the new Network Plus exam. But how did I get to this point? Well, back in college, I got my degree in electrical engineering. And when you're taking electrical engineering, you get to specialize in different areas, be it microcircuit design or power systems. Well, my specialty, my focus was on digital communication systems. So I took the microwave and the fiber optic and the digital signaling type of courses and labs. And right out of college, I went to work for GTE Laboratories. That was General Telephone's version of Bell Labs back in the late 80s. And it was a great exposure into just a lot of different telephony equipment. I did FCC and UL testing on various types of equipment and worked with key systems, PBXs, transmission equipment, POTS, plain old telephone service devices. Just a great introduction into the world of telephony. And then I went to work for a local university thinking I was going to be their PBX administrator, but to my surprise, they wanted me to build from scratch a data network centered around an old Cisco AGS Plus router. This is about 1989. It was running Cisco iOS 7.x, if you can imagine, and I fell in love with it. I started doing more and more with Cisco routers, and then later on in the 90s, Catalyst switches. Went after various certifications. First it was Novell, then Microsoft, and Cisco, and somewhere in there we did the CompTIA Network Plus certification, but I really have been focusing on Cisco for more than a decade. And you see some of my Cisco credentials on screen. I earned my CCIE in Route Switch back in 2001. And at the time of this recording, I'm studying for my second CCIE. I'm working on my CCIE Voice. I've already got my lab date scheduled, and I've already had one attempt, so I'm going after my second attempt right now. And one of the topics on that CCIE Voice lab is quality of service on a Cisco Catalyst 3750 switch. And it's interesting that if you go after the current Route Switch CCIE, instead of the 3750, that lab tests you on the 3560. The great news is, architecturally, when it comes to quality of service, they work the same. The same commands, the same architecture. I'll tell you a little bit about the difference between them coming up, but we'll see that there are a lot of similarities, so this video is going to apply to people going after their Route Switch or their Voice CCIE. But getting back to my biography and wrapping that up, after I had worked at the university for a while, I went to work for Walt Disney World down in Florida. If you know anything about my family and I, we're huge Disney fans, and I got to be one of 5 network design specialists down at Walt Disney World in Florida. My biggest project that I worked on, I got to help design and install the network that tied together the different theme parks, the Magic Kingdom and Epcot and Animal Kingdom and the studios and some of the resorts, based around Cisco gear. And Walt Disney World in in Florida, it was, and I think it still is, the largest single-site employer, at least in the United States. So I got to work on a very, very large-scale Cisco network, and that was a great experience. But now I've been teaching classes online, live Cisco courses, for over a decade. I've been writing Cisco Press books for about 8 years now, just loving what I'm doing. And like I said, I'm currently going after my voice IE, and primarily it's the voice courses that I teach. And I said that my experience went back to college. Well, to be honest, it goes back a bit further than that. I actually have a picture, no kidding guys, this is a picture of me at about 3 months of age. I'm in a telephone central office, an old step-by-step or a Stroger switch office, the one that clicks and clacks, the relays move as people dial digits. You see my dad, he's holding me there. He was a central office supervisor at the local telephone company for many, many years. So I grew up in and around a telephone office. I really think this is in my blood. It's my destiny to be teaching telephony, and I certainly love what I do. You see my milk bottle being warmed on a soldering iron in the background. And I'm really passionate about sharing what I know about telephony and learning more myself. And I thought, as I'm getting ready for my voice IE, this is an area that I really need to master. And I thought, if I did this video, not only would it help me master the topic, it could help a lot of other people as well, not just those going after the voice lab, but people going after the route switch lab as well. Because, like I said, the 3560 for the route switch lab and the 3750 on the voice lab, architecturally, when it comes to quality of service, they work the same. Really, the big difference between these two switches is that the 3750 supports Cisco's StackWise technology. With StackWise, you can have a stack of these switches interconnected with these special connectors to form a virtual 32 gigabit per second backplane, and you get to administer this stack of switches as if it were just one device. Think of the 3560 as more of a standalone version of the 3750. So when we talk about quality of service features in this training video, I want you to understand that what we're saying applies both to the 3560 and the 3750. Let's go ahead and get started talking about the quality of service features of these different switches. And we're going to simplify this and break quality of service down into these 4 different functional areas. We're going to talk about classification and marking together. Classification is recognizing different types of traffic, where the switch says, oh, you're this type of traffic, well, I want to put you in this queue, or you're this type of traffic, so I'm going to mark you this way. And by marking traffic early on in a packet's travel, the next router or the next switch can very quickly, very efficiently look at that marking and make a decision, like a forwarding decision or a dropping decision based on that marking. We'll talk about how that's done. Then policing can set a speed limit on traffic. If we don't want certain types of traffic to consume too much bandwidth, literally, we can set a speed limit on it. We can say, you are not allowed to exceed this limit, and here's what happens if you do. And if you're taking notes, and I hope you are, I'd like you to jot down that congestion management is queuing. Congestion management equals queuing. This is where we're determining how much bandwidth goes to different types of traffic. Which type of traffic goes first? Maybe voice traffic is high priority traffic. We want to put that in a priority queue. Congestion avoidance on a router uses something called weighted random early detection. On our switches, congestion avoidance refers to weighted tail drop, WTD. We'll talk about that as well. Those are the 4 main areas. And something you need to understand, there's going to be a lot of syntax in this presentation. But the good news is, if you just understand it conceptually, if you know what you need to do, you don't need to necessarily memorize the syntax. After all, in the real world, you've got access to Cisco documentation. In fact, in the IE labs, the voice and the route switch lab, you've got access there as well with the doc CD. If you're practicing, let me show you how to get to it from Cisco's website. If you just go under support, and if we go down to support and documentation and go into configure, this is approximately what you get on the lab. And if you want a quality of service configuration guide, you could go under products. Let's go under switches. We'll go into our LAN switches access. And again, the 3750, the 3560, when it comes to quality of service, it's going to be the same. Let's just go into the 3560 and let's click on configuration guides. And I'm just going to select what appears to be the most recent configuration guide. And there's a section in this configuration guide on configuring quality of service. So here it is. You can use this as your guide in the real lab and in the real world as well. So I wanted to set your mind at ease up front. You don't have to memorize all the commands that we're going to be giving you. I want you to understand what the commands do, why you need them, some of the subtleties about the commands, some areas to watch out for, but you don't have to memorize everything we're going to be talking about. Just want to set your mind at ease about that. Well, let's get started now with a discussion of classification and marking. The classifying traffic early on in its travel is really a Cisco best practice recommendation. Cisco tells us that we should classify and mark our traffic as close to the source as possible. And the reason is what I told you earlier. If we somehow mark traffic, maybe using a layer 2 marking like a class of service, a QoS marking, or layer 3 marking like a differentiated services code point, a DHCP marking, or an IP precedence marking. If we mark traffic early on, then the next router or the next switch, and the one after that, and the one after that, those devices don't have to go through all the work of reclassifying traffic, maybe with an access list. They can very quickly, very efficiently look at the existing marking on a frame or a packet and make a forwarding decision or a dropping decision based on that. The analogy I give is a gate agent at an airport. Let's say, like we see the lady on screen, let's say that I'm about to board a plane and I haven't actually reached the status yet, but I'm working on it. Let's pretend that I'm a frequent flyer. Now, I fly Delta Airlines a lot, and I'm a member of the Sky Miles Club, but I've not quite reached the medallion level yet, where I get to board early. But imagine the day finally comes. I've earned enough miles, I've flown enough places, and I'm finally a frequent flyer. Can you imagine the scene as I go up to the gate agent, and the gate agent says, "Mr. Wallace, before you board the plane early, can you just prove to me that you are a frequent flyer? Can you show me your boarding pass from the time you went to Austin and Chicago and San Jose and Orlando and on and on and on? And I've got to produce all these boarding passes from the flights I've taken over the past few years." That's not very efficient, is it? So how do I prove that I'm a frequent flyer? Well, what the airline does is they put a marking on my boarding pass. The way Delta seems to do it is they give you a zone number, and I think I've got it figured out. I think if you're in zone 2 usually, that means you're a frequent flyer. So I could just show the gate agent my boarding pass that it says zone 2, and because I have already been classified one time and marked, I have a marking on my boarding pass as zone 2, I get on the plane ahead of the other passengers, or some of the other passengers. First class still beats me on. But you get the idea. By classifying one time, it becomes more efficient the next time and the next time and the next time based on these markings. That's what we want to do. Let's talk about how we can do classification and marking on our Cisco Catalyst switch. The big thing you need to know up front as we take a look at our first piece of syntax is that quality of service by default is disabled on our Catalyst switches. And when I say Catalyst switches, remember I'm talking specifically about the 3560 and the 3750. If you have a different model, things might work a little bit different. Go into Cisco's documentation and check out the configuration guide for the model you have. But I'm trying to focus on the models that are going to be appearing on the route switch and the voice, i.e. labs. And I should also hasten to say that because this is a CCIE level discussion, I'm making some assumptions. I'm making the assumption that you already know your way around Cisco iOS. You're already familiar with the basics of quality of service. For example, I'm assuming that you already know about the 3-step MQC process where you create class maps to classify traffic, and then you create a policy map to say what you want to do with those different classes of traffic, and then you apply that policy map somewhere like an interface. I'm assuming you already know those basics. And if not, you might want to check out some of my other quality of service videos. You can go to my website, oneexamamonth.com. That's oneexamamonth.com. And if you go into the C voice area, there's a bunch of free QoS videos you can check out there. But assuming that you're kind of studying at the CCIE level, let's get back to the story. To turn on quality of service globally in our switch, we're going to say MLS QoS. And MLS, that stands for multi-layer switching. Don't try to read too much into that because even on something like a 2950 or a 2960 switch, we still might use that command even though it's not a multi-layer switch. That's just the command, MLS QoS, to globally turn on quality of service. And when we're doing classification, when we're recognizing different types of traffic, we could recognize that traffic and assign a policy to what we're going to do to that traffic at the port level as it comes in a particular interface, or we could do it at the VLAN level. Hopefully you're familiar with the concept of an SVI, a switched virtual interface. This is where you've got this virtual interface on a switch, and it's on that virtual interface that you configure an IP address, and you've got other switch ports on that switch that belong to the VLAN. Maybe you have interface VLAN 100, and you've got a bunch of ports that belong to VLAN 100. Well, you can do configuration in the interface VLAN 100 configuration mode, and that configuration applies to all the ports in VLAN 100. That's one way of doing classification and marking. That's VLAN-based classification. And if you want to do VLAN-based classification, you go into the interfaces, into the ports that belong to that VLAN, and you would issue the command we see on screen, MLS QoS VLAN-based. In fact, let me give an example of this. Let's first of all go into our switched virtual interface. We go into interface VLAN 100, and assuming we already have this policy that we're about to apply, we can apply the policy that I've just called test here. We can apply that policy to the SVI, to the VLAN interface. We're saying service policy input test. Notice we're applying it to the VLAN interface, not the physical ports. Then we could go into the ports that belong to VLAN 100. Let's say gigabit 1/0/7 like we see on screen. And in the port configuration mode, we could say MLS QoS VLAN-based, saying that it's going to take its quality of service policy settings from its switched virtual interface that controls its VLAN. We are going to be giving you an example of VLAN-based classification later on in this presentation, but primarily we're going to be focused on the port-based classification. In fact, what are some different ways that we can classify at the port level? We could classify based on layer 2 characteristics or layer 3 characteristics. Down at layer 2, we could look at a layer 2 quality of service marking, a CoS, a class of service marking. You see at layer 2, if we have, for example, an IEEE 802.1q trunk, there are 4 bytes that get added on to a frame, except for one VLAN in a .1q trunk. There's an untagged VLAN, that's called the native VLAN. But all the other VLANs, they get 4 bytes slapped on the end, and in one of the bytes there are 3 bits that are used to identify the priority of that frame. And how many possibilities does that give us? Let's see. 2 raised to the 3rd power is 8. We've got 8 different possible CoS class of service values, 0 through 7. Cisco says don't use 6 or 7. Those are reserved. And perhaps a frame coming into a switch already has a CoS marking. If it does, we can classify it based on that. We can put it in a certain queue based on that. We can remark it to a different marking based on that. We could have an access control list down at layer 2 that matches source and destination MAC addresses. That's another way of classifying traffic. We could classify at layer 3, the network layer as well, with an existing marking. In an IP version 4 header, there's a byte called the TOS byte, the type of service byte. And a byte, of course, has 8 bits. If we use the 3 leftmost bits to indicate the priority of that packet, that's called IP precedence. Again, with 3 bits at our disposal, that's 8 possible values. 2 raised to the 3rd power is 8. And again, Cisco says don't use 6 or 7, those are reserved. So we're dealing with the values in the range of 0 through 5. By the way, if we're trying to mark voice over IP traffic with an IP precedence value, the actual voice media, the best practice is to use an IP precedence of 5. And if we're marking at layer 2 with a CoS value, we should use a CoS of 5. In fact, our Cisco IP phone does that for us by default. A challenge with IP precedence, though, is that it's not very granular. I mean, we only have 6 values that we're supposed to work with. We might have more classes of traffic than that. So fortunately, there's the DHCP marking as well. That's what we typically use today. The DHCP marking is going to use the 6 leftmost bits in that TOS byte. That gives us many more possibilities. 2 raised to the 6th power is 64. We can have 64 different DHCP values. And that's almost too many, because if I just say, well, on my network, I think a value of 25 is awesome. That's what I'm going to use to mark my best traffic with. And I send it over to your network, and your network says, 25, that's not a very high priority in my network. I like 55. That's what's high priority in my network. You see, there's no common frame of reference. So the IETF did us a huge favor. The IETF standards body pre-selected certain DHCP values in the range of 0 through 63, and they gave them names. These names are called PHBs, per hop behaviors. And an example is the value 46 has the name of EF, or expedited forwarding. That's what we should be marking our voice media with. In fact, the Cisco IP phone does that by default. And we could classify based on an existing marking, like a DHCP value. Or we still could use an access list. We could use a numbered or named access control list at layer 3. So we've got these different ways of classifying traffic, but here's a potential challenge. What if we want to classify, let's say, based on a DHCP marking, which is in an IP packet, but the traffic coming into the switch is not an IP packet? How do we handle that type of classification? Well, even though that frame is not an IP frame, it still has a layer 2 header, and maybe it's coming over a .1Q trunk or even an ISL trunk. Maybe it has a CoS, a class of service value, or even an 802.1p value. Even if it's not coming over a trunk, you could still have a CoS value by using 802.1p, where 4 extra bytes get added to a frame. A lot of PCs do this. You can add 4 extra bytes to a frame, and you still have those 3 bits that are used to indicate a CoS value, except with .1p, you don't set the VLAN field. The VLAN field remains all zeros. It looks almost identical to an 802.1Q frame, but technically it's not. A lot of PCs can mark a CoS value using 802.1p. But back to our story. We've got this non-IP frame going into the switch. That non-IP frame might have a CoS value. If it does, then the switch is going to, by default, allow that frame to keep its CoS value. And I say by default, we've done MLS QoS on the switch. We've enabled quality of service. At that point, by default, the non-IP frame is going to keep its CoS value, even if we're classifying based on something else. However, if it does not have a CoS value already, it's going to inherit the CoS value of the port. We're going to see the syntax coming up for setting a port's class of service value. So in this case, we have a port CoS of 0, a layer 2 quality of service marking of 0. This frame without a CoS marking comes in, it gets remarked to the ports marking, which defaults to a 0. Here's how we set that port's CoS marking, maybe to a non-zero value. We can, in interface configuration mode, say MLS QoS CoS and give a value in the range of 0 through 7. Again, Cisco cautions us not to use 6 or 7. You might actually use 6 to mark routing traffic, but that's about it. Otherwise, you wouldn't want to use 6 or 7. And remember I said that by default, if a frame already has a CoS value, it's going to keep that value. Well, here's a way to alter that default. We could use the command MLS QoS CoS override. Override says, I don't care if you already do have a CoS value, I'm going to remark it with the ports class of service value. That's a way of overriding that. And we can also trust different types of markings coming into our switch. If I trust a CoS marking, for example, I might place the frame in a certain queue. I might also use that as the basis for remarking it to another marking. You see, here's a big challenge with CoS markings. A CoS marking is a layer 2 marking. Think about what happens to layer 2 information as it tries to cross a router. Think of a MAC address as it tries to cross a router. That layer 2 information is rewritten, isn't it? The router is going to rewrite the source and destination MAC address. Same kind of thing happens with the CoS value. The router is going to rewrite that CoS value to a 0. So even if we've done all this great design work up front to give our traffic the optimal CoS value that it should have, everything's just perfect, as soon as it crosses a router, it's blown away. It's back to 0. So we want to preserve some sort of relative quality of service marking, and what we can do is use a mapping. That's a big topic we'll talk about in a few moments. We could say, if then, if the CoS value is a 3, then set the DHCP value to maybe 24, because IP precedents, DHCP markings, these layer 3 markings, they can successfully cross a router boundary without being remarked. But Right now, we're asking the question, what marking coming into the switch is going to be trusted? A Cisco IP phone, for example, is going to mark voice packets with a QoS value of a 5 and a DHCP value of a 46, which again has the per op behavior name of EF, or expedited forwarding. And we could say what we trust. If we're coming in from the campus backbone, maybe we're trusting those layer 3 markings, but if we're coming into the switch port from a phone, we might want to trust a QoS marking. And we can trust, as you see on screen, with the command MLS QoS trust, a QoS value at layer 2, a DHCP value, or an IP precedence value at layer 3. In fact, we could even put a qualifier on this. We could say, I want to trust this marking if and only if it came from a Cisco IP phone. Maybe we don't want to trust a QoS marking coming from an end user's PC who happens to be running a network interface card that supports 802.1p. Now, we only want to trust the marking if it comes from a phone. Here's what we could do to enforce that. We could say MLS QoS trust and say what we're trusting. Here I'm using QoS, but we don't stop there. We give an additional qualifying command. We say MLS QoS trust device Cisco-phone. Now, a lot of people get confused on this. They think that they could just give the bottom command. They could just say MLS QoS trust device Cisco-phone, and that's sufficient to trust a QoS value if and only if it comes from a phone. No, that's not going to do it, because we might be trusting a DHCP value if it came from a phone. So you have to give two commands to make this happen. The first command to say, what are we trusting? And the last command to say, we're only going to trust that marking if it came from a Cisco IP phone. By the way, how do you think the switch knows that this marking came from a phone? How does it know that a phone is directly attached? Think about it for a second. What would allow a Cisco switch to know that a Cisco phone is attached? How about the Cisco Discovery Protocol, CDP? That would do it. Specifically, CDP version 2 is what we want to run, and the Cisco Discovery Protocol is going to let the switch realize that a trusted device is attached to that port. And we were talking a few moments ago about how we could take one marking, maybe a QoS marking, and remark it to some other value, maybe to a DHCP value, and this could be based on a mapping table. Let's think about how that works. If we want to see the existing mapping tables in a switch, we could give a command like this. We could say show MLS QoS maps, and there are lots of options here. If you just give that command by itself, it's going to show you all the different mapping tables in the switch. Here, though, we're just focusing on the QoS to DHCP mapping. We're saying show MLS QoS maps QoS-DHCP, and notice how we can interpret the output. We have all 8 QoS values listed, 0 through 7. And just below the QoS values, we see the DHCP value that the switch is going to use to mark that packet. Frame comes in with the QoS value of a 0. Well, that packet's going to be marked with a DHCP value of a 0. A QoS of 1 is going to be marked with a DHCP value of an 8. A 2 is going to be marked with a 16, or in our example, notice how this works. We've got a QoS value of a 3 coming in, but based on the mapping table, we're going to mark that packet whose layer 2 header has a QoS value of a 3 in it. We're going to mark it with a DHCP value of 24, something that can survive a router hop. I mentioned that there were several different mapping tables that we had available. We can get a sense by doing some context-sensitive help. We could say show MLS QoS maps, and we see that we can map from QoS values to DHCP values. We could do something called DHCP Mutation, where we say if we come in with one DHCP value, we're going to mutate that into another DHCP value. Something later we'll be talking about is policed DHCP values. We can say if traffic is going too fast, if it's exceeding our speed limit, that we could mark it down based on this particular mapping. So lots of different options. We don't want to make this an exhaustive discussion of every possible option, but this does give us a sense of what different mapping tables are available. Let's take a look at how we might configure one of these mappings ourselves if we want to alter the default behavior. We could say MLS QoS map, and we see the different things that we could set up a mapping table for. And let's say that we want to do a QoS to DHCP mapping. On some switches, it might not be optimal. On some Cisco Catalyst switches, a QoS value of a 5, used for our voice over IP traffic, is going to be marked to a DHCP value of a 40. We would prefer a 46. So sometimes this is something we would want to do. In fact, I'm giving you the command on screen that is a best practice for mapping QoS to DHCP values, especially for the voice world. We say MLS QoS map QoS-DHCP, and notice I'm giving 8 values. Those 8 values are 8 DHCP values, but they correspond to the 8 COS values, 0 through 7. So a COS value of a 0 is going to be marked with a DHCP value of a 0, that first value. A COS value of a 1 is going to be marked with a DHCP value of an 8, a 2 with a 16, a 3 with a 24, a 4 with a 32, and here's the big one I want you to notice. A COS value of a 5 is going to be marked with a DHCP value of 46. That is what we want for our voice over IP media traffic. We can then verify that the mapping was successful. We could do a show MLS QoS maps COS-DHCP, and we saw how to interpret this previously. You can see the COS value and the corresponding DHCP value. By the way, I said that the values I gave on screen represented a best practice. Here's an easy way to remember this, especially working with voice traffic. Here's how you should set up your COS to DHCP markings. Really simple. You might want to capture it in your notes. You start out with a 0, and then you give multiples of 8 with one exception. And that one exception is when you get to a 40, instead of using 40, use 46. Other than that, it's multiples of 8. So you start with 0 and then use multiples of 8. So 0, 8, 16, 24, 32. Here's the exception. Instead of a 40, give a 46 and then continue on with your multiples of 8, 48 and 56. So start with 0, multiples of 8, the exception, use a 46 instead of a 40. And to give you another QoS value mapping example, let's talk about DHCP mutation. This is where we tell the switch if you come in with one value, one DHCP value, we're going to give you a different DHCP value. To set this up in global configuration mode, we define a DHCP mutation. Here's the command up at the top of the screen, MLS QoS map DHCP-mutation, give it a name. I like to use all uppercase lettering in my names, by the way. That way when I'm looking through a config, I can very quickly spot a name that I came up with. So if I see uppercase demo, I know that's not some sort of Cisco iOS keyword. That's something that I came up with. So I'm calling this mutation demo. And then I'm giving a series of DHCP values, 24, 26, 28, 30. If a packet comes into the switch with any of those DHCP values, I'm going to mark it to a DHCP value of 24. We then go into interface configuration mode. I say that I'm trusting DHCP markings, and I apply that mutation, which is called demo. And then I'm looking at my DHCP to DHCP mutation map. Notice that right within interface configuration mode, I don't have to exit back out. I could just say do and then give a command. I could say do and then something like a show command. I'm saying do show MLS QoS maps DHCP-mutation, and here's the way you interpret the output. You have the incoming DHCP value and then you have the outgoing DHCP value. Your incoming DHCP value is going to be broken into 2 different digits. In my example, let's say that we want to take a 26 and see how it's being mapped. We're going to find the 2 in 26 along that left-hand column. If we go down 3 rows, you see there's a row for the number 2. And then we look at the column with the header of 6, and we see where that 2 row and the 6 column meet. The 2 row and the 6 column, they meet at a value of 24. That's a way for us to interpret that output, that a DHCP value of a 26 is going to be mutated to a DHCP value of 24. And that's going to wrap up the first part of our discussion dealing with classification and marking. Again, just to sum up, we want to keep this simple. We said that we could classify, we could recognize different traffic at layer 2 using a MAC address access control list or using a COS marking. We could classify traffic at layer 3 with an access control list or an existing DHCP or an IP precedence marking. And once we recognize that traffic, we could do something with that traffic. Maybe we could take one marking and convert it into another marking. And as we're going to see later, those values are going to be used for policing, congestion management or queuing, and congestion avoidance or weighted tail drop. And we saw how to influence how those mappings happen. Oh, and we also saw how to turn on QoS globally on our switch with the MLS QoS command. So at this point in our discussion, we've enabled quality of service on our switch. We're saying what marking, if any, we're trusting on incoming traffic coming into a port. and we saw how to take that marking and maybe remark it to another marking. But at this point, has the behavior of anything really changed yet? No. No, now we need a mechanism to look at that marking and make some sort of a decision based on that marking. The first mechanism we're going to consider that does that is policing. Policing is going to set a rate limit for a certain type of traffic. Metaphorically, we could think of this as a speed limit. And if traffic obeys that speed limit, we've got traffic not trying to exceed that speed limit, it's referred to as conforming traffic. If we have traffic that exceeds that speed limit, that's called exceeding traffic. Exceeding traffic, we could say it's going to be dropped. If you're violating the speed limit, you're discarded. You're out of here. We're going to discard you in the bit bucket. Or we could say, well, we'll still try to send you, but we're going to punish you. You exceeded the speed limit. You got to pay a fine. We're going to mark you down to a lower priority DHCP value as an example. In fact, that's what we're seeing here on screen. Based on whether traffic is obeying the speed limit or not, we can transmit it, we could drop it, or we could transmit it and remark it with a different value. And remember earlier we talked about the fact that classification could be turned on at the port level or at the switched virtual interface level. Policing can be turned on there as well. We can turn on policing at a port or under interface VLAN something, under the SVI. And we'll take a look at the syntax for doing both. First, let's consider policing a port. When we're policing traffic at a port, we can do it based on a single class of traffic. We could say that we're going to classify FTP traffic. And if that file transfer protocol is taking up too much bandwidth, we can start discarding excess packets. Or we could say we're going to set a speed limit, but it's not for a single class of traffic. It's for lots of classes of traffic combined. If the combined bandwidth of multiple classes of traffic, if that exceeds a certain speed limit, then we're going to start maybe dropping traffic. If we're doing that, if we're policing based on the total bandwidth consumed by multiple classes of traffic, that's called an aggregate policer. Let's take a look at our first example, and we'll keep this one simple. Let's police based on a single class of traffic. And again, I said earlier that I was making the assumption that you were already familiar with MQC, the Modular Quality of Service Command Line Interface. If not, this is a great example of MQC. It's a three-step process. Step one, we classify with the class map. Step two, we say what we're going to do with the class of traffic with a policy map. And step three, we apply that policy map typically to an interface. First, we are going to recognize a certain type of traffic. In my example, I'm recognizing voice media traffic, which in the Cisco world uses UDP ports in the range of 16,384 through 32,767. Notice up top, it's a good old-fashioned access list. Access list 100, I'm permitting, in other words, I'm matching that range of UDP ports. And then I do step one of MQC. We go into a class map, which are called VoIP, and I'm saying I want to match access group 100. That's going to match that access list. So now my voice packets, they get classified into this VoIP class map. That's step one of MQC. Step two of MQC says, so what do you want to do with this class of traffic? To do step two of MQC, we create a policy map. I'm saying policy-map police-VoIP. Not much happens, by the way, in policy map configuration mode. The magic happens in policy map class configuration mode. Notice that our config mode goes from PMAP to PMAP-C when I say class VoIP. Now we're in policy map class configuration mode. I'm saying, what do I want to do with this particular class of traffic? And I'm saying police, and I'm giving a number of 256,000 followed by a number of 8,000, and then I say exceed-action drop. Let's camp out here for a moment and understand what's going on. We said that policing could set a rate limit on a certain type of traffic. Well, that rate limit, in this case, is 256,000 bits per second. Some quality of service configurations use a unit of measure of kilobits per second. When it comes to policing, though, it's bits per second. Careful with that. And the 8,000, that's even more confusing. The 8,000 is not a rate. This is not bits per second or bytes per second. It's nothing per anything. It's not a rate. It's just a number of bytes. Let me explain what we're saying here. It's called the burst size. Let's take a step back and think, though, how do we send at a rate that is less than the interface speed? If I've got a gig port and I'm policing my voice traffic, in this case, to 256K, how is that even possible? How can I send traffic at a rate that is less than the port speed? It seems physically impossible. Well, the secret is this. We don't send all the time. We send a certain number of bytes at line rate and we stop. And then we send a certain number of bytes at line rate and we stop. We start and we stop, we start and we stop, and then over time, over the period of a second, on average, we've sent, in our case, 256 kilobits per second. Here's a metaphor to help you understand this. Let's assume that after I shoot this video today, I'm going to hop in my car and I'm going to go visit a friend. And let's say that that friend lives 60 miles away. And I hop in the car, I'm anxious to get there, and I drive at a rate of 120 miles per hour. At that rate, how quickly would I be getting to my friend's house? 30 minutes. At a rate of 120 miles an hour, I would cover a 60-mile distance in 30 minutes. And at that point, my car would be stopped. But let's say that along the way to my friend's house, I get pulled over by a law enforcement official. And they say, "Mr. Wallace, do you realize you were driving at a rate of 120 miles an hour?" I could accurately say that, well, actually, officer, no, I wasn't. I was driving at a rate of 60 miles per hour. You see, over the period of an hour, I would only have traveled 60 miles. I traveled at a rate of 120 miles an hour for 30 minutes, and then I traveled at a rate of 0 miles per hour for the next 30 minutes. So over the period of an hour, on average, I traveled 60 miles per hour. Okay, don't try that in the real world, but that is the way it works with policing. With policing, we're going to send at line rate for a period of time, and we're going to stop. We're going to start and stop and start and stop. The value of 8,000 on screen, that's how many bytes we're going to send when we are sending at line rate. We're going to send 8,000 bytes at line rate, and then we're going to stop, and then we'll send another 8,000 bytes at line rate, and then we're going to stop. But if you take a look at this over time, you will see that on average, we will be sending at an average rate, not an instantaneous rate. If we had one of those police radar guns that we could hold up and check the speed of a packet coming out of a port, it wouldn't be 256K. It would be a gig or whatever the line speed was. But on average, over time, it would average out to 256K because we're not sending all the time. The 8,000, that's our burst size. That says how many bytes we send at one time before we take a break and don't send anything for a while. Normally, this is not a value that we need to be terribly concerned with. It's not changing the speed limit. It changes how bursty we're going to be sending traffic. If I made this a much, much larger value, then I would be potentially sending at line rate for a fairly long amount of time, and everybody else might have to wait on me to send at this rate. So traffic that's not being policed, it might be delayed while I'm transmitting my traffic. However, I give other traffic types more opportunities. I let them transmit more frequently. I give them a smoother bandwidth utilization by picking a smaller number. I typically use 8,000. So again, when we say police 256,000, we're saying that is the rate limit. And the way we get to that rate limit, it's an average over a period of time. The way we get that average rate is we send at line rate and we stop. We send and we stop. And when we're sending 8,000 bytes at line rate, and then we're stopping. And then we send another 8,000 bytes. And over a period of time, on average, we're sending at an average rate of 256K. Then we say, what do we want to do with this exceeding traffic? Traffic that's trying to be transmitted in excess of 256K. And here we're saying we're going to drop it. Another option might be to try to transmit it, but mark it with a lower DHCP value. But here we're saying we're going to drop it. That's step 2 of MQC. Step 3 of MQC is when we take this policy map and we apply it typically to an interface. Here we're saying in interface gigabit 1/0/8, we're applying this service policy coming into the switch. As traffic is coming into this port, we're saying if your voice traffic, welcome. If your average rate is not greater than 256K. If it is greater than this excess voice traffic, it's going to be dropped. Let's take this a step further. Let's say that we want to police not just a single class of traffic, we want to police a collection of traffic types. Notice that in our first command on screen, I'm saying MLS QoS aggregate-police. I'm giving an aggregate policer name. This is just a name I came up with, VoIP media signaling. And I'm setting an aggregate rule. And that aggregate rule is giving a rate limit of 320 kilobits per second, 320,000 bits per second. That's the aggregate policer rule. And then we're saying that the rate limit for all the traffic types that fall under this aggregate policer, the rate limit for everybody combined, is 320,000 bits per second. Again, I'm giving 8,000 as my burst. I'm going to be sending 8,000 bytes at line rate. Maybe it's a gig, maybe it's 10 gig, but I'm going to send 8,000 bytes at line rate, and then I'm going to stop. I'm going to send nothing, and then I'm going to send another 8,000, and I'll send nothing. I'll start and I'll stop, I'll start and I'll stop, and over a period of time, on average, we will send no more than 320,000 bits per second. Any exceeding traffic, it's going to be dropped. But instead of applying this to a single type of traffic, notice, I'm defining two types of traffic. And sticking with my voice example, I'm identifying RTP, the real-time transport protocol traffic, which is a range of UDP ports. Cisco uses 16,384 through 32,767. I'm matching that with an access list. And then I'm also matching call setup traffic, specifically the Skinny Client Control Protocol, SCCP. And I'm creating an access list. I'm using a named access list here called SCCP, where I'm recognizing that call signaling traffic. And I create a couple of class maps, one for RTP, one for SCCP. Then I create a policy map. Notice how this works though. When I go into policy map class configuration mode for RTP and I say police, I'm not saying police and then giving a rate limit. I'm saying police aggregate, and then I'm giving this aggregate rule of VoIP-media-signaling. I'm doing the same thing for the SCCP class. That means that you're going to be part of this aggregate total amount of bandwidth that all these different classes are going to use. In this case, I've got two classes assigned to this aggregate policing rule. What this means is the grand total amount of bandwidth, RTP and the Skinny Client Control Protocol traffic combined, their combined limit is not allowed to exceed 320,000 bits per second. And if it does, we're going to drop that exceeding traffic. And again, step 3 of MQC, we're applying it to an interface down at the bottom of the config. And let me show you one other policing example, and this is going to tie into what we discussed earlier about those quality of service mappings. One mapping that we could have is a policed DHCP mapping. A policed DHCP mapping says if traffic is exceeding the rate limit that we specified, if that traffic has any of these DHCP values, let's remark any of those DHCP values to this other value. So notice the first command on screen. I'm saying if we have DHCP values of 24 or 26 or 46, by the way, 24 and 26 commonly used for call setup packets, and 46 used for actual voice media packets. If we are exceeding our rate limit, we could say if you have any of these values, we're going to remark you to a value of 0. And again, a little bit repetitive from our previous example, I'm creating a class map for RTP, a class map for SCCP, but notice when we get into policy map class configuration mode for RTP and for SCCP, notice I'm saying for RTP, for the real-time transport protocol, police to a rate limit of 256,000. And the way we're going to get there, we're going to send 8,000 bytes, and we'll stop, and we'll start, and we'll stop. Not a big deal. That does not affect our overall rate limit. That just impacts how bursty our transmissions are going to be. The exceed action is not drop in this case. The exceed action is policed-DHCP-transmit, which means we're going to go look at this globally defined mapping, which says if your value is 24 or 26 or 46, and it's probably going to be 46 if we're talking about RTP traffic, we're going to mark you with a DHCP value of a 0. Same thing for the SCCP traffic. And step 3 of MQC, we apply that to an interface. So here we're setting up this global rule that says if you violate the speed limit, instead of just giving an exceed action of drop, we can say, no, we're going to remark you to this other value. There is another policing example I want to give you, and it deals with policing an SVI. This is where we're going into interface VLAN something, and we're applying a policy map there. It gets a little tricky here, guys, we're going to have a nested policy map. Remember when I was reviewing MQC a few moments ago? I said that step 1 is we create a class map to recognize traffic. Step 2, we create a policy map to say what we want to do with those different classes of traffic. And step 3, we apply the policy map. And I said that we typically do that to an interface. Well, another place you can apply a policy map is not to an interface. You can apply it to another policy map. You can apply a policy within a policy. That's a nested policy map. And that's what we're going to have to do here. We're going to apply a policy map to the interface VLAN something, the SVI. That particular policy map is not going to contain the police command. Instead, it's going to reference another policy map. And that other policy map, the nested policy map, the child policy map, some people would call it, that's going to contain the police command. Let's take a look at an example. First, remember what we discussed early on in this presentation. We were saying that if we wanted to do VLAN-based quality of service, then we would need to go into the interfaces participating in a specific VLAN. Let's say it's VLAN 100, and we would need to say MLS QoS VLAN-based. That's what we're doing at the top of the screen. We're going into a range of ports, gigabit 1/0/15 through 20, and for that range of ports, we're saying they're going to be using VLAN-based quality of service. Then we start to go through the 3 steps of MQC. We have an access list that's matching RTP traffic again, and that traffic gets classified by the RTP class map. And I've got another class map that this time, instead of matching a particular type of traffic, it's matching the input interface. We're giving that range of ports as the ingress interface for traffic. And then we're creating what we're going to refer to as the child policy map. I named it port, and we go into policy map class configuration mode for the ports class map. Remember, that's the class map matching this series of ports, and we're saying for traffic coming into this port, we're going to police it. We're going to set a rate limit to 256,000 bits per second with a burst of 8,000 bytes. The exceed action is drop, which is pretty much what we saw before. Here's where it gets different, though. We're not going to be able to take that policy map of port and apply it directly to the SVI. That would not work. Instead, we have to nest it inside of another policy map. So now we're going to create a parent policy map that we've named VLAN. And we go into the RTP class, not the ports, but the RTP class for the VLAN policy map, where we're matching that range of ports. And notice it's within policy map class configuration mode of that parent policy map, where we say service-policy port. That's referencing the child policy map. That's the policy map that sets the policing rate limit. Now also notice that I'm saying set DHCP 46. I'm marking this RTP traffic coming in these ports with a DHCP value of 46. You might think, well, the IP phone is already doing that, no need to do it here. Actually, you've got to do something in this policy map, because when you try to apply it to your SVI, if all you've done is say service policy port, it's going to say you're not doing anything. You didn't configure anything in that policy map. So you've got to do something. And the something I'm doing is I'm setting the DHCP value on these voice packets to 46. Understanding they're probably already 46, but it's not going to do any harm to set it to 46, and I have to do something, or else I'm not going to be able to apply it. Then we can finally do the 3rd step of MQC, where I go into an interface. In this case, it's an SVI. It's a VLAN interface, and I say service-policy input, and I give the name of the parent policy map VLAN. This is going to police RTP traffic entering that range of ports to a rate limit of 256,000 bits per second. And it's going to mark that traffic with a DHCP value of 46. And that's going to wrap up the discussion of the second quality of service feature on our Cisco Catalyst switches that we mentioned. We've now talked about classification and marking. We've talked about policing. And in your notes, I ask you to write down that congestion management equals queuing. Let's talk about that next. I gave you a fairly intimidating bullet list of things that we might have to configure. This is where a lot of people really get confused with quality of service on these models of Cisco Catalyst switches. there are so many things to configure. We can set up a priority queue. We can define something called a queue set. We can say how many buffers are going to be available for sub-queues. How much memory can they possibly allocate? What thresholds are we going to have for dropping traffic? What CoS or DHCP values go into different queues? How do we give different amounts of bandwidth to these different queues? How can we limit the amount of bandwidth that a queue has available? There's a lot to do here. However, we're going to try to simplify this and really break it down into two major functions. The first function is all about getting our queues configured, defining a priority queue, saying what type of traffic goes into the various queues. You see, if you think about the input or the output interface on a switch, that interface, that port, has a buffer, a queue allocated to it. And it can take that queue space and we can carve it up into sub-queues. We can have a couple of sub-queues going into a switch. We have 2 input queues, and a port can have 4 output queues. And we can put different types of traffic in those different queues. And we can set some limits, some thresholds to say, well, if the queue isn't at all congested, we're going to put all these different CoS values in the queue. Maybe we'll put in CoS values of 0, 1, 2, and 3. But if the queue starts to get congested, if we exceed 25% of the queue capacity, for example, maybe we start rejecting certain types of traffic. Maybe we start rejecting CoS 0 and 1 traffic. That's something we can do with our threshold settings and weighted tail drop. So one big task that we have is just laying the groundwork, defining our queues, defining what goes in the queues, defining these thresholds. That's job one. Let's set everything up for the input and output queues. Then once we do that, the second task we have is to say how much bandwidth are we going to give to those different queues. That's going to use a technology called shaped round robin, or SRR. And you'll notice the graphic I have on screen. This is a graphic of the Splash Mountain entrance at Walt Disney World. One of my daughters and I, we were about to go on this ride, and I took this picture, and I was thinking that this represents what we're about to talk about. Because on Splash Mountain, I remember we had to stand in line for, it was about 40 minutes, I think, before we could get on the ride. And we stood in, literally, it was called a queue. You stood in this big line that weaved and wound around these trees, and eventually we got on the ride. But some people got on the ride a lot quicker than we did because they had something called a fast pass. You could go in and you could request a fast pass for this ride early on in the day, and it says, okay, come back between these times. You get to get in a priority queue. And if you have this special pass, you're able to show it to the cast member, and you're able to get in this shorter queue. You're able to get on the ride sooner. That's what we can do with our traffic inside our Cisco Catalyst switches. We can give some traffic a fast pass. We can give it access to this priority queue where that traffic gets to go first, out ahead of some of the other types of traffic. We could loosely compare that to a priority queue in our Cisco Catalyst switches. And that's going to be one of the big concepts we're going to need to understand. Let's get started, though, by taking a look at the architecture of our queues coming in and going out of our Cisco Catalyst switch. We mentioned that we had an ingress queue. Coming into a port, we can have 2 queues. Notice when we come in, we can classify traffic. We could apply our policing rule. If we're going to do any marking based on that policing rule, we could do that here coming into the switch. And then we're going to put that traffic in one of 2 queues. And one of those queues can be a priority queue. And by default, after we've enabled quality of service on our switch, by default it's queue number 2. Queue number 2 is the priority queue, meaning it's going to get preferential treatment. And I gave you the comparison to the Fast Pass at Walt Disney World. Another comparison often used is the carpool lane. If you're in a large city and there are 2 or more passengers in your car, you're a special type of traffic. You might be able to get over into this leftmost lane called the carpool lane, and in times of congestion during rush hour, you might be able to go ahead of a lot of the other traffic. It's really congested in those primary lanes, but you're in this special carpool lane. You're in this priority lane. You're a special type of traffic, and you get to go ahead of other types of traffic. But here in America anyway, is that carpool lane like the Autobahn? Is it unlimited speed? Can you go as fast as you want? No, there's still a limit. You can still only go so fast. And the same thing holds true with the priority queue. We're going to be able to empty that priority queue out first ahead of the other queues up to a certain limit. You see, by default on the ingress coming into the switch, that priority queue has access to 10% of that port's bandwidth. The first 10% of that port's bandwidth, if we have traffic in that priority queue, you bet it's going to get to go first, and it's going to be able to consume as much as, but no more than, 10% of the interface's bandwidth. So we're not going to be starving out other traffic types. Once we place traffic in one of these incoming queues, we're going to be able to configure SRR, and I know I define that as shaped round robin. Well, it could also be known as shared round robin, and in the input queue it has to be shared round robin. We'll distinguish between those later. But we can run this shared round robin algorithm to dictate how we're going to empty traffic from these queues and send it to what I think of as the backplane of the switch. They're referring to it here as the stack ring. This is going to interconnect the incoming port with the outgoing port. And if there's a lot of congestion on a switch, and there can be congestion on a switch due to speed mismatches, we might be coming in, for example, at a rate of 10 gig and leaving at a rate of fast Ethernet. That's a pretty big speed difference. Even on a high-speed Cisco Catalyst switch, we can still have congestion. And if we're not able to get to the backplane, if we're not able to send from the source port to the destination port right away, well, the good news is we can store that traffic temporarily in one of these two input queues coming into the switch. Let's contrast this with our egress or the output queues coming off of the backplane or coming off of the stack ring going toward that outbound port. Instead of just having two queues, we had two input queues, we can have four output queues. We have this grand total queue space that gets carved up into four outbound queues. And again, the way we're going to empty those queues is based on how we have SRR configured. And in the outbound direction, SRR could be either shaped round robin or shared round robin. And again, we'll talk about the distinction between those in a bit. Also, we could have one of these queues defined as a priority queue, a queue that gets serviced first. Not unlimited, but up to a point, it could have priority treatment, but not to the point of starving out other traffic, hopefully. And it's important to understand that on the Cisco Catalyst 3560 and 3750 switches, this is not true for all switches, but for those models of switches, it's queue number 1 that could potentially become the priority queue. It's not enabled by default, but it can be enabled, and we're going to show you how to do that. In fact, let's think for just a moment about how we can configure priority queuing. For our input port, the ingress port, we said by default queue number 2 was our priority queue, and it was limited to 10% of the interface's bandwidth. We could send traffic in that queue first, up to a limit of 10% of the interface's bandwidth before we started allowing other types of traffic to flow. If we wanted to alter that behavior, here's how we would do it. In global configuration mode, so this is going to impact the ingress queue for all of our ports, we can say MLS QoS SRR-Q input priority-Q, and you get to say which queue is going to be the priority queue. It's 2 by default. You could still leave it at 2, or you could set it to a 1. Then we could set a bandwidth amount. In the example on screen, I'm saying queue number 1 is going to be my priority queue, and I want the bandwidth to be 20% of the interface bandwidth. So my final command is MLS QoS SRR-Q input priority-Q1 bandwidth 20. Globally configured, I'm making Q1 my priority queue instead of the default of Q2, and 20% of the interface's bandwidth gets to go first. It's going to get priority treatment, kind of like a carpool lane, but that's the speed limit of the carpool lane. We're not going to be able to exceed that amount of bandwidth. We're not going to just keep sending traffic from the priority queue at the expense of other traffic types. How do we enable outbound priority queuing for our egress port? Here, it's not defined globally, it's defined in the port, in the interface itself. If we give the command priority-Q out, that is going to transform queue number 1. Remember, we had 4 outbound queues. Well, queue number 1 of those outbound queues in a port is going to be transformed into a priority queue. Notice that this command is not being used to specify a bandwidth limit. We'll get to that a little bit later. But these commands that we've just seen They show us how to configure or manipulate the priority queuing configuration of our ingress, our incoming, and the egress, the outgoing queues. Before we get into SRR and all of that configuration, we need to jump ahead and talk about the fourth of our 4 quality of service topics, and that was congestion avoidance. And I said that that was going to be using something called weighted tail drop. We need to understand that because we're really going to be configuring SRR and weighted tail drop together. So we need to understand the theory of both of them before we get into the config. The idea is this. Within one of our queues, let's say our outbound queue is divided into those 4 sub-queues like we talked about. Let's say that this is queue number 1 of those sub-queues. And in our case, we'll pretend it's not acting as a priority queue. What we could do is say different QoS values are going to be placed in this queue. But as that queue starts to fill to capacity, we're going to start denying admission to certain QoS values. Here's the way to interpret the graphic on screen. As long as we're not congested, everybody is welcome in this queue. And to make it simple, I'm just putting all of our QoS values in this one queue. Everybody is welcome until we hit 25% of the queue's capacity. At that point, QoS values of 0 and 1 and 2 are going to be rejected. Newly arriving frames that have a QoS value of 0, 1, or 2, they're going to be turned away. Everybody else still gets to come in until we hit 50% of the queue depth. At that point, we're going to start rejecting QoS values of 3 and 4, in addition to 0, 1, and 2. But QoS values of 5 and 6 and 7, they're still permitted until we get completely full. When a queue completely fills to capacity, obviously there's no room in the queue. Newly arriving frames are going to be dropped off the top. That's called tail drop, by the way. That's a good term for your notes. Tail drop is when a newly arriving packet or frame is dropped because there's simply no room in the queue. At that point, all of our traffic is going to be dropped. And notice that we've defined 3 thresholds on screen. Threshold 1 and 2, we could administratively configure where those thresholds lie. I just randomly picked 25% and 50%. We could set those to different values. But the third threshold, threshold number 3, that is the capacity of the queue. That doesn't change. And our Cisco Catalyst 3560 and 3750 switches, they're going to have these 3 thresholds. We've got 2 input queues, 4 output queues, and we can have 3 thresholds. It's important to understand that as we're thinking about the architecture of these Cisco Catalyst switches. And at this point, you're probably starting to see that there are a lot of moving parts when it comes to congestion management and congestion avoidance. We've got thresholds, and it's going to get even more complicated. We're going to see in a few moments that we'll need to set up how much buffer space is going to be available for a queue. And it can go above that, but we can set a limit on how much it can possibly exceed its guaranteed capacity. We could give different amounts of queue space to different queues on an interface. And that's a lot of configuration, isn't it? To go into each of our ports and say, well, here's your thresholds, here's your guaranteed buffer availability, here's your maximum memory, here's your buffer allocation. Wow, that's a lot of work to do on every single interface. So here's a shortcut. You're going to like this. We're going to be able to configure, it's kind of like a macro. We're going to define something called a queue set, and we can define these types of parameters for not just a single interface, but for a queue set. And then we can assign ports to that queue set. And by default, all of our ports on a switch belong to a single queue set 1. But there is a second queue set that we can configure. If we want some of our ports configured differently than other ports, we could define a second queue set. And the way you assign an interface or a port to a queue set, you see it on screen, we say queue-set space, and we give the queue set ID, which is going to be either a 1 or a 2. Again, everybody belongs to queue set 1 by default. And in that queue set, we can define thresholds and buffer availability and on like you see on screen. But if we need a separate set of rules, we can define queue set number 2 if we need to. Let's talk about one of the things that can be defined for a queue set. When we think about a physical port on our Cisco Catalyst switch, there is a chunk of the switch's memory that's going to be dedicated to the output queue for that port. And remember, we're going to take the grand total queue space for that port, and we're going to carve that queue space up into 4 separate queues. We're going to be able to place different types of traffic into different queues. And we can give each of those 4 queues a certain amount of memory. Maybe we want queue number 1 to have a greater capacity than queue number 2. We're going to be able to specify the allocated amount of memory for each of these sub-queues. And just because we allocate a certain amount of memory for one of these sub-queues, that doesn't necessarily mean that it's guaranteed to have that amount of memory available during times of congestion. We can specify what percentage of that allocated memory is guaranteed to be there in a pinch. If we're congested, do we guarantee that 100% of that queue's allocated memory is going to be there? We could do that, or we could say, well, I allocated you this much memory, but if times get tight, I'm only going to guarantee that you can have 75% of that. So we can set a different percentage of the memory allocation that we give to one of these queues. We can specify what percentage is guaranteed. It doesn't have to be 100%. And then we could say, well, if you need even more storage space than we've guaranteed you, it's possible that you can go above that. Because notice how the memory is laid out. Each of our ports have these 4 queues. I've illustrated a couple of ports on screen, ports 1 and 2. They each have 4 queues. But in addition to the queue space dedicated for these ports, there's this common memory pool from which we can borrow. So we could literally say that a queue can have more memory than its capacity simply by borrowing from the common memory pool or from some other queue that isn't using its memory at the moment. We could do something like this. We could say, well, I guarantee that you're going to get 100% of what we've allocated for you, but if you need more and more is available, maybe you can have as much as 200% of your allocation. Let me show you this graphically. Notice on screen port 1 queue number 2. Here I've said that this queue can have a maximum of 200% of its memory allocation if it needs it. And what's it doing? It's borrowing from the common memory pool. I have the areas shaded in. Not only is it using the memory dedicated to port 1 Q2, it's also using an equal amount of memory from the common memory pool. Here's the syntax for how we can set this up. In global configuration mode, we're going to say MLS QoS Q-set output, and we identify the QSet ID. Everybody belongs to QSet 1 by default, but if we've divided it up, we could say the QSet ID might be a 2. We can also specify those thresholds here for weighted tail drop. We could say threshold, and we say for a certain queue, Q1 for example, it could be 1, 2, 3, or 4, drop threshold 1 is 25, and drop threshold 2 maybe is 50. And then I can say, what is the reserved threshold? Is this going to be 100% of the memory allocated to this queue? Is it going to be something less than that? And then I can say, what is the maximum threshold? Maybe it's 200%. It's double the memory that was allocated for that queue. And we've been talking about allocating an amount of memory for a queue. Here's the command that lets us do that. Not all queues are necessarily created equal. We could give different storage capacities to our different queues. We've got these 4 output queues. We could use this global configuration command to size those queues differently. MLS QoS Q-set output. Again, we give the QSet ID, and we're going to specify the number of buffers that we have available for each of our queues. And in the example on screen, it looks like I'm giving queue number 1 33 buffers, queue number 2 17 buffers, queue number 3 and queue number 4 25 buffers. The valid range for the number of buffers is 0, if we don't want to use the queue, 0 through 99 for queues 1, 3, and 4. There's kind of an exception though for queue number 2. Queue number 2 has to have at least 1 buffer available. That's used by the CPU. So it has a minimum of 1 and therefore a maximum of 100. We've seen a lot of syntax now. Let's tie this together and make some sense of it by walking through an example. Here we're saying in that first command, MLS QoS QSet output 2, we're defining something for QSet 2. Nobody belongs to that by default, so we'll need to put a port in that QSet. But we're saying for QSet number 2, we're divvying out the memory like this. 50, 25, 10, 15. That's the relative amount of memory that's going to be given to these different queues. And if we add that up, 50 plus 25 plus 10 plus 15, that's really convenient. That adds up to 100. That means that 50 out of 100, 50% of the port's buffer space is going to be given to Q1. 25 out of 100, 25% of the port's buffer space is going to be given to Q2, 10% to Q3, 15% to Q4. That's the buffer allocation, but that's not guaranteeing that that queue is going to have access to that much in times of congestion. Remember, we could set the guaranteed reservation amount, and then we could set the maximum amount that we could potentially allocate by borrowing from the common memory pool or borrowing from another queue that doesn't need its memory at the moment. That's what we're doing in the next command. We're saying MLS QoS Q-set output to threshold to 33, 66, 100, 200. What this means is when we say QSet output 2, that's QSet 2. Then we say threshold 2, that's talking about queue number 2, 2 of our 4 queues. For queue number 2, our first drop threshold is going to be 33% of the capacity of the queue. The second drop threshold is going to be 66%. Remember, there is a third threshold. We don't configure that here, because the third threshold, by definition, is the entire queue space. When the queue is completely full, we have reached the third threshold. What's up with the next two numbers, though? 100 and 200. Well, the 100 means that 100% of the buffer space that we've allocated to Q2 again is going to be guaranteed to be there. Even in times of congestion, guaranteed it's going to be available. By the way, what is that guaranteed queue space? 25 buffers. We see that in the top command. What's the 200 in that second command? Well, that says we're going to be able to use some unused buffer space from another port or from the common memory pool if we suddenly need more than 25 buffers in queue number 2 during a time of congestion. We just gave the one command here for queue number 2. We might give similar commands for queues 1 and 3 and 4. And this configuration was for QSet 2. By default, nobody belongs to QSet 2, so notice what we're doing toward the bottom of the config. We're going into interface gigabit 1/0/11, and we're saying, hey, you belong to QSet 2. And now, that interface, that port, it suddenly inherits all those configurations. Something we've not done yet, though, is to say what traffic is going to be placed in the different queues. We said, here's the buffer allocations for the queues. Here's how much is going to be guaranteed during a time of congestion. Here's the maximum amount of buffers that a queue could possibly allocate if it needed more than its original allocation. But we've not yet said what kind of traffic goes into these queues and what traffic is going to fall in these different thresholds that we've set up. That's what this command on screen is going to do for us. Let me just walk you through the example. By the way, there are more options to the command you're seeing on screen, but I wanted to show you just the command that we need to accomplish what we're talking about right now. I just showed you those parameters. Well, I actually showed you one more. I showed you how we could map a QoS value or a DHCP value into a certain queue. But I think we can make the most sense of this by taking a look at the example. We're saying MLS QoS SRR-Q output QoS-map. We're taking a look at a frame's class of service value, and based on that frame's class of service value, we're going to put it in one of these 4 outbound queues, 1, 2, 3, or 4. And in the top command, we're saying Q1 threshold 1, 0, 1. What are we saying here? We're saying for queue number 1, QoS values of 0 and 1, they're going to be permitted into that queue until we reach threshold 1. And on the previous slide, we saw how to set the threshold for a queue. We could set 2 thresholds. We set up the threshold for queue number 2. I think it was 33% and 66%. Here we're dealing with queue number 1, though, and we're saying whatever that threshold is set to, QoS values of 0 and 1 are welcome to come in until we hit that first threshold. The next command, still dealing with queue number 1, says that QoS values of 2 and 3, they're going to be welcome until we hit the second threshold. The third command on screen says for queue number 2, we're going to allow a QoS value of a 4 to enter the queue until we hit the first threshold. Next, for queue number 3, we're saying a QoS value of a 5 is going to be permitted until we hit threshold number 2. So no effect from threshold 1. It's only until we hit threshold number 2 that we're going to start discarding a QoS value of a 5. And finally, queue number 4, it's going to be accepting QoS values of 6 and 7 until we hit threshold number 2. Here's that same command, but I've graphically shown you what we're doing. I drew out the 4 queues for you on screen with the thresholds. That top command on screen where we're saying Q1, threshold 1, 0, 1, for queue number 1, we're saying 0 and 1 are QoS values that are welcome to come into the queue until we hit threshold 1. At that point, we'll start rejecting those QoS values. The next command, the second command on screen, says for threshold 2, we're going to accept QoS values of 2 and 3. They're going to be welcome until we hit that second threshold. At that point, we're going to start dropping those QoS values. The third command on screen is dealing with queue number 2. It's only going to be accepting a QoS value of a 4, and then we're going to start dropping that QoS value of a 4 after we hit threshold number 1. The fourth command on screen is for queue number 3. We're going to be accepting a QoS value of a 5 in queue number 3 until we hit a threshold of 2. And the final command on screen for queue number 4 says we're going to be accepting QoS values of 6 and 7 into that queue until we hit threshold number 2. We've now completed the first of 2 major chunks of configuration that we were talking about earlier. We said that when it comes to congestion management and to congestion avoidance, we've got to lay the groundwork. We've got to go in and define the buffers that are available for our different queues, how much is reserved, how much is guaranteed during a time of congestion for the different queues, how many extra buffers can a queue have in a time of congestion if buffers are available maybe from the common memory pool or from another queue. We've defined the thresholds. We said, where are we placing different QoS values? We've now laid the groundwork, but we haven't yet said, how are we going to start emptying these queues? What amounts of bandwidth are we going to give to the different queues? That's where SRR comes in. SRR has 2 different modes of operation, shaped mode and shared mode. Shaped mode is only going to be working on the outbound, on the egress queues. Shared mode will work either inbound or outbound, or both. But shaping doesn't just give a guaranteed amount of bandwidth to a queue, it sets a limit on that bandwidth. It says, yes, you can have 20% of the interface speed, but no more. We're not allowed to go above that shaped limit. Shared, however, says, yeah, we're going to guarantee that you can have 20% of the interface bandwidth, but if you need more and more is available, we're not going to limit you to that. We're going to allow you to share with other queues. So to sum up, shaped not only gives us a guaranteed amount of bandwidth for a queue, it says that we can have no more than that amount of bandwidth, while shared says you can have a guaranteed amount of bandwidth, and maybe more if you need more. Let's begin our discussion of the configuration of SRR by taking a look at our input queues. And remember, only shared round robin, not shaped round robin, is going to be used on the input queues or the ingress queues. First, this command is fairly similar to what we saw with our output queues. We're setting the drop thresholds for our input queues. In this example, we're saying for queue number 1, the first threshold is 25% of the queue capacity, and the second threshold is at 50% of the queue capacity. Again, the third threshold, by definition, is 100% of the queue capacity. Also similar to what we did with our output queues, we can say what buffer allocation, what storage capacity, not bandwidth, but what storage capacity is going to be given to our 2 different queues. We say globally, and notice we're not using QSets here. QSets, that's a concept that we use outbound only. Here in global configuration mode, without referring to a QSet, we're saying MLS, QoS, SRR-Q input buffers 2575. We're saying that 25% of a port's buffers are going to be given to queue number 1. That's the size of the queue. That's its capacity. That's not necessarily the amount of bandwidth it's going to have. That just influences how much traffic it can hold. 75% of a port's buffers is going to be given to queue number 2. And finally, we get to SRR. Here's how we say how much bandwidth, not storage space. The buffer option specified the storage space. The bandwidth option here on screen specifies the percentage of actual bandwidth that we have available. And we're giving a guarantee of at least 30% of a port's bandwidth to queue number 1, and a guarantee of at least 70% of a port's bandwidth to queue number 2. That was our input queues. Let's take a look at the output queues, however. Remember, with output, we can use shared mode or we can use shaped mode. First, we're going to take a look at shared mode. And very similar to what we just saw with our input queue, we can specify 4 weights, the relative amount of bandwidth that's going to be given to these 4 queues. And in our example, we have a relative weight of 30 for queue number 1, a relative weight of 20 for queue number 2, 25 for queues number 3 and 4. Notice that if we add those numbers up, 30 and 20 and 25 and 25, it equals 100. It doesn't have to. I like to do it that way. I think it makes it a lot easier to visualize the bandwidth percentage that's going to be given to a queue, because remember, it's a relative weight. In other words, take a look at the number 30. It's 30 relative to the grand total of the weights for all the queues. So if we add all the queues up, we just said that's 100. Well, queue number 1, therefore, is going to get 30 100ths. In other words, 30% of that port's bandwidth. You don't have to make them add up to 100. They could add up to something else. If they added up to 200, then it would be 30 divided by 200. That would be the percentage. What would that be? 15% of the port's bandwidth that would be given to Q1. But just as a good practice, you might want to make your weights add up to 100, just for your own convenience. And also notice that unlike our input queue configuration, the output queue configuration for SRR, it's configured not globally, it's configured in interface configuration mode. Let me give you an example. Here we're going into interface gigabit 1/0/4. It's got a speed of 1 gigabit per second. The speed is 1000 meg, is what we're saying there in that second command. And we're saying that the bandwidth for shared round robin is 10, 25, 35, 50. Does that add up to 100? No, it doesn't. Let's see, we've got 50 plus 35 is 85, plus 25 is 110, plus 10 is 120. But we said it didn't have to be 100. We can still use that total as our denominator in this ratio, in this fraction. We can say that the bandwidth for queue number 1, it's a relative weight. It's going to be the value of 10 divided by everything else total up. 10 divided by, what do we say the total was? I think it was 120. And if we take that number and multiply it times the interface speed, that's going to give us the bandwidth available to queue number 1, which is going to turn out to be 83.3 megabits per second. For queue number 2, it's 25 divided by 10 plus 25 plus 35 plus 50. In other words, 25 divided by 120 times 1000 megabits per second. That's going to give queue number 2 a bandwidth of 208.3 megabits per second. And you see I've done the same calculations for queues number 3 and 4. And if you add up all those bandwidths that we have calculated on screen, they should add up to the interface bandwidth of 1000 megabits per second, and they do. That's a good check to make sure that we did our calculation correctly. That was shared mode, but now let's take a look at shaped mode. This is a bit more confusing. Now we're not dealing with a relative weight, we're dealing with an inverse weight. And I didn't say inverse relative weight, it's just an inverse weight. In other words, the value given to queue number 1 has nothing to do with the value given to queue number 2, and that has nothing to do with the value given to queue number 3, and so on. Let me show you what I mean. We say that the inverse weight is 1 divided by whatever value we give. I've given a value of 50 for queue number 1. What would its inverse weight be? Well, what is 1 divided by 50? It's 0.02. If I multiplied 0.02 by an interface speed of 1000 megabits per second, a gig in other words, that would be 20 megabits per second. So again, you take that value and you calculate the inverse. In other words, 1 divided by that number. 1 divided by 50, 0.02, times 1000 meg gives us 20 meg. We're saying that queue number 1 can have, guaranteed, 20 megabits per second, but no more. Remember, shaped mode sets a speed limit. We're saying you cannot go over this amount. We're doing the same thing for queue number 2, 1 divided by 50. In other words, 2% of the interface speed is going to be available to queue number 2, but no more. And we're simply not applying any shaping at all to queues number 3 or 4. And notice the tip I'm giving you on screen. I'm pointing out that if we configure an interface for both shaping and sharing, and we've got numbers set up for queue number 1 for both shaping and sharing, which one wins out? Well, it's the shaping configuration that's applied. And the sharing number, whatever it is, it's going to be ignored. This is one of the more challenging concepts in our Cisco Catalyst quality of service. I want to walk you through some examples. We've already seen one example of shared round robin. Now let's take a look at shaped round robin. Here, for an interface speed of 1000 megabits per second, we're saying SRR-Q bandwidth shape 30000. In other words, we're not doing shaping for queues 2, 3, or 4, but how much bandwidth are we given to queue number 1? It's the inverse. It's 1 divided by that number. It's 1 divided by 30 times 1000. That's going to give us 33.3 megabits per second of bandwidth, guaranteed to be available if it needs it, guaranteed to queue number 1, but no more. Because we're saying shaping, we're putting a speed limit on that bandwidth. And we said we had the option of combining the two. This is an interesting example here. Again, for a gigabit interface speed, we're giving both a sharing and a shaping configuration. Let's make some sense out of this. We're saying that the sharing config is 100, 100, 40, 20, and the shaping config is 50, 50, 00. Remember what we said would happen if we had conflicting instructions? We have a relative weight of 100 assigned to queue number 1 for sharing, and we have an inverse weight of 50 assigned to queue number 1 for shaping. What do we believe? What do we do? We go with the shaping number. We completely ignore that 100. That number could be 50, it could be 200, it doesn't matter. It's ignored completely. We're going to pay attention only to the shaping value of 50. And it's an inverse weight. Notice the calculation on screen. When we're calculating the bandwidth guaranteed, and it's also the bandwidth limit for queue number 1, it's 1 divided by 50 times the interface speed. 1 divided by 50 times 1000, that's going to be 20 megabits per second. Guaranteed. If it needs that much, it's guaranteed to have 20 megabits per second, but no more for queue number 1. It's the exact same calculation for queue number 2, you'll notice. And then for queue number 3 and 4, there are no shaping values, so we get to use the shared values, but here's where it can be a bit tricky. We've got values of 40 and 20. Remember, it's a relative weight. It's 40 divided by, we said everything else totaled up. Well, is it 40 divided by 100 plus 100 plus 40 plus 20? No. We completely ignore those 100s. They were overridden by our shaping configuration. Since they are completely ignored, they're not even used in this calculation. When we're determining the relative weight for queue number 3 and 4, the denominator is only going to be 40 plus 20. We don't pay any attention to the two 100s because, like I said, those were overridden. So the calculation for queue number 3 is going to be 40 divided by 60, 40 plus 20. And we don't take that amount and multiply it times the interface speed because there have already been some reservations deducted from the interface speed. Remember, queue number 1, guaranteed 20 megabits per second. Queue number 2, guaranteed 20 megabits per second. We cannot include that in this calculation. So we have to take 40 divided by 40 plus 20, and we multiply that not times 1000, we multiply it by what's left of that 1000 after we deduct the 20 meg for Q1 and the 20 meg for Q2. So it's really going to be 40 divided by 40 plus 20 times 960. If you do that math on a calculator, that's going to give you 640 megabits per second. Similarly, for Q number 4, it's going to be 20 divided by, it's a relative weight, 20 divided by all these sharing weights, which in our case are only 40 and 20. So 20 divided by 40 plus 20 times the interface speed less the bandwidth reservations made by the shape option. So it's not 1000 we're multiplying by, it's 1000 minus 20 minus 20, 960. If you do that math, that's going to give you a bandwidth for queue number 4 of 320 megabits per second. Again, we can do our sanity check to make sure we calculated this correctly. Let's add up the bandwidth guarantees and limits for queues number 1 and 2, 20 plus 20. Let's add on to that the bandwidth guarantee for queue number 3, and let's add on to that the bandwidth guarantee for queue number 4, 320. That, great news, that totals up to 1,000 megabits per second, 1 gigabit per second. And in these examples, we've been assuming that the interface speed of 1,000 megabits per second, that's the value we've been using, we've been assuming that we're allowed to use all 1,000 megabits per second, all 1 gigabit per second for our output bandwidth. It doesn't have to be that way. By default, there's not a limit, but we could set a bandwidth limit, not for a queue, but for a port. For an interface. We can go into interface configuration mode and we can say SRR-Q bandwidth limit and specify a weight. Here we're specifying a weight of 85. That's going to limit us to 85% of the interface speed. So if we had issued this command when we were doing our shaping and our sharing calculations, we would not have been multiplying times 1,000 or whatever the number was. We would be multiplying times 850 instead of 1,000. Let's take a look at how we can do some verification and troubleshooting on our Cisco Catalyst switches. And a big word of caution, this is something I ran into on the Catalyst 3750, and I assume it's the same for the 3560. The command that I was used to giving on my routers to get packet and byte counts that were matching a class map and were having a policy applied, I used to give the command, and I still do on routers, show policy-map interface followed by the interface identifier, and it would show me how traffic was being classified, what the policy was, and the number of packets and bytes that were being matched by a class map and having the policy applied. You don't get packet and byte counts. That they show up as zeros if you give this command on your Catalyst switch. Something to be aware of and not to be freaked out by. Just be aware that that's the way it works. There are some commands that we can give, though. We could say show MLS QoS. This is going to tell us that QoS is indeed enabled. We could take a look at the port's trust configuration by saying show MLS QoS interface and giving the interface ID. This is going to tell us what are we trusting? Are we trusting anything? What is the port's class of service value? Are we using DHCP Mutation? And so on like you see on screen. Another command we could give, show MLS QoS interface followed by the interface ID followed by the keyword of policers, and this can tell us if we're doing any policing and what the rate limit is on a port. We also talked about the benefit of having a queue set for our output queues. We could have a different set of values for our buffers, for our thresholds, for our reserved amount, for our maximum amount. We could see those values for those two queue sets with this command, show MLS QoS Q-set. Let's now take what we've learned and tackle a couple of sample lab tasks. Let's challenge ourselves. In our first task, we're being told that on switch SW1, interface gigabit 1/0/10, we need to limit the incoming RTP traffic. That's already telling me policing. Let's limit that to 128 kilobits per second. Traffic that exceeds that should be remarked to a per hop behavior of CS1, class selector 1, and we're going to assume that RTP traffic originated from a Cisco IP phone. That piece of information right there tells us something. That tells us that RTP traffic is going to be marked. It's going to be marked with a class of service of a 5. It's going to be marked with a DHCP value of a 46. So how do you think that we might want to tackle this? Let's go out to our live interface right now, and I'm going to suggest that we use that policed DHCP mapping that we had. We can set up a rule like this. Let me show you. Let's go into global configuration mode, and let's say MLS QoS map policed -DHCP. Let's say if we originally had a value of a 46, we want to police that. We want to remark that to an 8. Only in the event that we're exceeding this rate limit that we specify. Now let's create an access list that's going to recognize the RTP traffic. Access list 100 permit UDP any, and this is going to be in a port range of 16.384 through 32.767. Let's go through the 3 steps of MQC. Let's say class-map RTP, and we're going to match that access list by saying match access hyphen, we don't say access list, we say access group to match it, and it had a number of 100. Step 2 of MQC, we create a policy map, and let's call it task 1. and we go into Policy Map Class Configuration mode, and let's set up our policing rule now. Let's say police, and we want to set a rate limit according to our task of 128,000 bits per second. We can specify a burst value. The minimum value we can specify is 8,000. That's fine. That's not going to impact the rate. That just impacts how bursty our traffic is going to be. How long are we going to have a sustained burst at line rate? And to make things a bit smoother, I like to use the minimum value. After we specify that, we can say, what is the exceed action? What do we do in the event that RTP traffic is exceeding this limit? We could say we're going to drop it, or we could say let's apply this globally defined policed DHCP map. Let's say policed DHCP transmit. Let's mark the traffic down and let's send it on its way. Step 3 of MQC is we need to apply this to an interface. Let's go and interface, I think it was gigabit 1/0/10, and let's say service -policy, and we're going to do this as we're coming into the switch, service policy input, and we give the policy map name of task 1, and we're done with task number 1. Let's check out task number 2. Here we're being told that on switch SW1 on gigabit 1/0/11, which is operating at a rate of 1 gigabit per second, we need to perform the following tasks. We want to enable the outbound priority queue. Remember what queue that is? It's only queue number 1. It's queue number 2 inbound, it's queue number 1 outbound. We need to put QoS 4 traffic into queue number 3 at threshold 1. In other words, we're going to put it into queue number 3, but after we exceed that first threshold in queue number 3, we're going to start discarding QoS 4 traffic. And we also want to limit the bandwidth of traffic leaving queue number 2. Let's limit that to 40 megabits per second. So we've got a few different things to do here. Let's think about what we have to do. Number 1, we need to enable the priority queue for that interface. We saw the command to do that earlier. We also want to set up a QoS mapping. We want to put a QoS value of a 4 into queue number 3 at threshold number 1. And finally, we want to use shaped round robin to limit queue number 2 to 40 megabits per second. So we might have to do a bit of math to make that work out. But let's get started. Let's begin by going into interface gigabit 1/0/11, and let's say priority -q out. That's the first thing we had to do. We had to make a priority queue out of queue number 1. We've done that now. Now let's set up that QoS mapping that we talked about. The command for that was mls QoS SRR-Q output, and we're going to be placing traffic not based on a DHCP value, but based on a QoS value. So we say QoS-map, and we're going to say this is a configuration for queue number 3. And for threshold number 1, we're going to be placing in a QoS value of 4. QoS 4 goes into queue number 3, but only until the point where we hit threshold 1. And the final thing we had to configure, we wanted to limit the bandwidth on queue number 2 to 40 megabits per second, given the fact that our interface speed was a gigabit per second. Remember, when we're setting up shaped round robin, we're going to specify a percentage of the port speed. Remember, it goes like this. We're going to go into interface gigabit 1/0/11, and we say SRR-Q bandwidth shape, and I'm not limiting anything for queues number 1, 3, or 4, so I'll put in a 0 for those values. But for queue number 2, I need to put in a percentage. So the question is, what percentage of 1,000 meg is 40 meg? We've got to do a bit of math. Let's take a look at the algebraic equation we're going to have to solve. We're going to have to say that 1 divided by x, remember it's a relative weight, it's 1 divided by some number that we're going to give here. 1 divided by some number multiplied by the interface speed of 1,000 megabits per second is going to equal 40 megabits per second. How do we solve that? Well, we can start by multiplying both sides by an x. That's going to give us 1,000 equals 40x. And then to find x, we're going to say that x equals 1,000 divided by 40. Let's bring up our calculator and say 1,000 divided by 40. That's a value of 25. X equals 25. That's the weight that we need to specify. Let's say that the inverse weight for Q number 2 is 25, and we're not doing shaping for Qs 3 or 4. We'll just put in zeros for those values. And that's going to complete task number 2. Did you understand how we did this command? We're saying we're going to shape Q number 2 to 40 megabits per second. How do we know it's 40 megabits per second? It's 1 divided by 25 times the interface speed. In fact, let me bring the calculator up again and prove this is correct. If we say 1 divided by 25, we get 0.04. And we multiply that times the interface speed of 1,000 meg, 1,000. That's going to give us 40 megabits per second. That was our task. Well, guys, hopefully you enjoyed that somewhat challenging lab task. And as we wrap up this discussion of quality of service on our Cisco Catalyst 3560 and 3750 switches, I want to make sure that this is not the last time we come in contact. If you want to keep in touch with me, that would be fantastic. I've got tons of free certification resources available at my website, oneexamamonth.com. Explore that. You're going to find dozens and dozens of free training videos. Also, if you're into Facebook, you can like my fan page. You can like Kevin Wallace Networking on Facebook. You can follow QoS CCIE on Twitter, or you can subscribe to QoS CCIE. That's my YouTube channel. And I just want to say thank you so much for entrusting me with about 2 hours of your time. I hope that I've been a good steward of that time, and I certainly wish you the best in your real-world deployments as well as your certification pursuits. Take good care, everyone. Hope to see you soon.